So now let's talk about the composite face changing materials. So basically we use composites face changing materials to tailor properties. So composite PCMs is a material which has an active phase and passive phase. So we have more than one phase, and one of the phase acts as PCM. So it's another way of having encapsulation. So we have an active phase. So the active phase has lower melting temperature and worst thermal conductivity. The passive phase has high melting temperature and good thermal conductivity. So basically we are coupling the material with worst thermal conductivity to the material with good thermal conductivity to maintain the temperature stable as possible. So but only one of this phase can act as PCM. So which phase? Let me write it. But only one phase can act as PCM. So we see that the passive phase will have no transition in the service temperature range. So we are interested in this. So which it can have high structural properties to withstand more stress. So but we have an active phase which is behaving actually as PCM. So basically the active phase behaves as PCM. So by arranging the active and passive phase in different ways, we can actually tailor a lot of the properties of our component. So first thing, we can change, let's say, the way in which our active phase is distributed inside of the sample. So we can change the results and the thermal behavior of our component. And also we can change the mechanical properties of our PCM parts. So let's investigate a little bit what happens inside our material if we have the given unit cells. So imagine to them be repeated in several times to form a rectangle and to see what happens in terms of thermal response. So we had different thermal response by changing the arrangement of the unit cell. So there is also another factor, how coarse is our structure. How coarse is our structure. So imagine that we have our form. Let me suppose you have cubic unit cells and we are going to repeat in many direction to build something 4x4 or 2x2 patterns, which is going to look something like this. It is arranged in all parts. Okay, so it's 4x4x4 lattice cells. So first thing we have to Okay. So, okay. So this is a foam. So imagine that we have our foam, and when we have coarse foam, the difference in temperature from one point to the other point will be larger. So because we have more space. So when we have really coarse or big amount of liquid inside our structure, we can have also another phenomenon, which is conductive motion of molten material, due to which we can promote heat transfer. The problem is that in this case, the direction from which heat is supplied is affecting the convective motion. So it will be affected. So it will affect the heat transfer of our system. So as an example of composite PCM, we can be found by looking at some particular kind of alloy that are immiscible alloys. That are immiscible alloys. So various research have used an alloys having a miscibility gap. So we have two different phase diagram. So like copper Fe combination or bismuth copper combination. So these alloys are immiscible. At low temperature, we don't have solubility of one element in the other. Now let's focus on in copper Fe system. So in copper Fe system, the iron has BCC structure and copper has FCC structure. So when we increase the temperature of the active phase, which is copper, because it has low melting temperature, because the copper has low melting temperature, it acts as the active phase. So this is active phase. So when we increase the temperature of the active phase, which is copper, we see that in liquid actually we have a quite low solubility of iron into copper. So we can say that for certain temperature range, actually the copper in liquid form is pure copper. There is only minor amount of iron in the solution. So the same can be seen in bismuth copper system, where bismuth has low melting temperature. So this acts as an active phase. But we have no solubility of both elements and at room temperature. So liquid bismuth will be pure. So what happens when we solidify this alloy? So when we have solidification of this alloy, we have said that the copper is active phase and iron is passive phase. Since iron start to solidify at high temperature, we will have solidification of iron and segregation of copper. So basically we have segregation of copper and solidification of iron. So copper forms small spheres. So copper forms small spherical aggregates. In liquid form inside the iron. Inside the iron. So at the end of the solidification, we have spheres of copper surrounded by iron. So in this case, we end up with a perfect PCM material. So our PCM material will look something like this. I will draw the diagram. Okay. So this thing is Fe passive phase, and this is our copper active phase, which is spherical aggregates. And we are going to obtain perfect PCM for copper Fe system. Now in copper, so the problem is it doesn't work like this for most of the material, like for obtaining the perfect PCM thing, like in this fashion. So in copper bismuth system, the solidification will start with copper dendrites. So solidification will start from copper dendrites. So in this case, instead of spherical aggregates, we are going to get copper dendrites. For instance, we have segregation of bismuth. So which is the last element to solidify? So this is the bismuth is the last element to solidify. So we have bismuth matrix surrounded by copper. So it will look something like this. Let me draw. So this is our copper. Sorry, this is passive phase. Copper passive phase. And this is our bismuth active phase. This is for copper bismuth system. So if bismuth is melting, it's not stable. It will leak everywhere. So the nice thing is that bismuth has good wettability on copper. So bismuth should have good wettability on copper. So we can use this material as PCM. So PCM is able to stable even if the bismuth is melted, simply because of good wettability. Now let's talk about the another system which can be considered as PCM. We can say it's aluminum tin system. So in this case, SN has low melting temperature. So this will act as an active phase. So the solubility of aluminum and tin is practically 0 up to 300 degrees Celsius. Solubility of aluminum in tin is 0 up to 300 degree Celsius. So we are able to use tin as PCM up to this temperature. So we have a problem in this case that the microstructure is not like copper Fe. So we don't have spheres of tin surrounded by aluminum. It is more similar to bismuth copper system. The microstructure is similar to copper bismuth system. So we have one problem in this case also, because tin has not good weldability with aluminum. What is the problem with this case? Tin has not good weldability with aluminum. So how can we solve this issue? So we can solve this issue by using a rapid solidification. So we can change something. Other possibility is to mix different material. Other option is to mix different material to solve this problem. So we can start with aluminum powder, mix those with tin powder, compact it, sinter it, and we can get the island of tin, which is I think brighter phase, surrounded by aluminum. So its microstructure is similar to basically copper bismuth system. So in the next lecture, we are going to study about the how can we develop the PCM material and how can we characterize the PCM material. So for now, thank you.